Hello, friends. Welcome back to my YouTube channel. Today, I will be discussing stage-wise leaching. Since last few videos, I have been discussing stage-wise leaching, and in part number 6 of my discussion on leaching, I will discuss multi-stage cross-current leaching. So, in this video lecture, I will discuss how to write material balance for a 3-stage cross-current leaching operation, and then how to follow this material balance equations on the equilibrium diagram. So at the end of this discussion, you will be able to write material balance for a 3-stage cross-current leaching, and then you will be able to follow that material balance on an equilibrium diagram. So let us start today's discussion. To begin with, let us know something about stage-wise contact, and for that we will consider a simple ternary system. Feed is a mixture of solids B and C. C is the solute to be separated by leaching, whereas B is the insoluble solid and it is called the carrier solid. So feed is containing two solids, solid B and solid C. Solid C is to be separated by leaching, therefore it is the solute, and the other solid, that is B, it is insoluble solid, and you can it is called the carrier solid. The solvent used in this case it will be denoted by capital A. So you have a system of A, B and C, three components, A, B and C. This is the feed mixture and it is contacted with the solvent. The feed mixture, that is B plus C and solvent A, they are contacted in a stage-wise manner. So by stage-wise contact, we mean that the feed mixture B plus C and the solvent A, they are contacted in a stage-wise manner. And in order to simplify the analysis, you may assume some things. The following may be assumed. Solid B is not soluble in solvent A. You can assume that out of B and C, only C is soluble in A, whereas B is not at all soluble in solvent A. Solid B is not at all soluble in the solvent A. Then the second assumption is there is no preferential adsorption of either solute C or solvent A on the surface of the solid B. So you may assume that when C gets transferred to A, so you have A plus C, which is a liquid solution, and this liquid solution will be in contact with the solid phase, which will be containing B and some unrecovered solute C in it. So when the liquid and solid phase, they are in contact with each other, there is a possibility of C getting adsorbed on the solid surface or A getting adsorbed on the solid surface. So in order to simplify the analysis, what you can do, you can assume that there is no adsorption of C, there is no preferential adsorption of C on the solid surface, or there is in the same way there is no preferential adsorption of A on the solid surface. So this is the second assumption. And the third assumption that you can use is the quantity of solvent A is enough to dissolve all solute C in it. So whatever solute C is present in the solid mixture, the quantity of solvent used, the quantity of A used is such that it can dissolve, it will have a potential of dissolving all C in it. So then if this is assumed, or if this is true, then an equilibrium will be established between the liquid phase and the solid phase. So for simplification, you can make these three assumptions. Solid B is not soluble in the solvent A, no preferential adsorption of either solute C or solvent A on the surface of the solid B. And the third assumption is the quantity of solvent A is enough to dissolve all solute C in it. Now each stage that is used in stage-wise contact, it should have the following provisions. There should be a provision for mixing solid feed mixture with the solvent, and there should be provision either for settling or filtration or drainage of the resulting slurry of insoluble solid B emerges in the solution of solute C in solvent A. So when the solid phase is mixed with the liquid phase, there is formation of a slurry, and we need to either settle the slurry or filter the slurry or drain the slurry. So there should be provision for either one of these three in the stage. So first there should be provision for mixing, and then there should be provision for settling or filtration or drainage. So if you have to understand it with the help of this schematic diagram, the feed mixture which is containing B and C, it is contacted with the solvent A, and within the stage you will have a mixing operation, that is there will be mixer which is followed by a settler. I have shown over here I have shown settler. So instead of that you may use filtration or drainage. So this will separate the clear solution which we call overflow, which is nothing but solution of A and C, and the underflow, which is also called leach solids, and it will be containing B, plus it will also contain some amount of solution A plus C. So there will be insoluble solid B plus some amount of clear solution of A and C will also be present in the underflow. Why this is true? Because it is not possible to separate, it is not possible to have perfect separation of overflow and underflow. A perfect separation would be the one where you will be able to separate all A plus C solution from the underflow. But in reality, it is impossible to have perfect separation. That's why in the underflow, there is some quantity of the clear solution of A and C that will remain in the underflow. Now, as per requirement, you can use multiple stages. These multiple stages, they can be arranged in a desired cascade of multiple stages. It is nothing but an arrangement where multiple stages are arranged so that an output from one stage is an input to the next stage. I have discussed this concept in my discussions on liquid extraction. So cascade, you can have similar cascades in leaching also. So in a cascade, in a typical cascade, multiple stages are arranged so that an output from one stage is an input to the next stage. I will shortly show you how they are arranged. Now in leaching also, the two common cascades that are used, one is cross current cascade and the other one is counter current cascade. So in this video and in my next video, I will be talking about cross current cascade, and then I'll talk about counter current cascade. So today we will understand how leaching is carried out in a cross current cascade. Now leaching in cross current cascade, when leaching is carried out in counter current cascade, you call it as multistage cross current leaching. And in this case, how the operation is carried out in this case, the underflow is successively contacted with fresh solvent in multiple stages. In this case, the underflow will move from one stage to the other, and in each stage it will be contacted with a fresh solvent. It will be clear to you when I'll show you the schematic diagram. For time being, you just understand, in a multistage cross current leaching operation, the underflow is successively contacted with fresh solvent in multiple stages. This could be carried out batch wise or in a continuous manner. Now let us understand this let us consider a 3-stage cross current leaching. That is, we are going to consider a cascade, a cross current cascade that has 3 stages in it. And in this case, the feed mixture is B plus C and solvent is A. And this feed mixture and solvent, they are contacted in a 3-stage cross current leaching operation. And it could be carried out in a batch wise manner or in a continuous manner, I have told you. Now let me show you the schematic diagram. Now the circle that I am drawing, each circle is going to represent one stage. You know that. I have discussed it in liquid extraction. So this circle represents stage 1. Circle number 2, it represents stage 2. Circle number 3, it represents stage number 3. Feed is admitted to stage number 1. And it will be described by this quantities. I'll shortly tell you what are this. So feed is admitted to stage 1 and then it is contacted with a fresh solvent stream. And at the end of leaching in this stage, you'll be getting an overflow and you'll be getting an underflow. The underflow will be transferred to the second stage, where it will again be contacted with a fresh solvent. At the end of the operation in the second stage, you'll get overflow from the second stage and then underflow from the second stage. Underflow from the second stage, it is sent to the third stage, where it is again contacted with a fresh solvent stream. Then finally, stage number 3 will produce an overflow and it will also produce an underflow. So in this way, a 3-stage cross current operation is carried out. Now, our next task is to know what are the notations that I have used in this discussion. So let us understand what are these notations. So finally, you are going to get the final underflow, then final overflow from stage number 3. Okay, now let us understand the notations that I have used. For feed, I have used F, and F represents mass or mass flow rate of A plus C in the feed. Mass if it is a batch operation, mass flow rate if it is a continuous operation. So F represents mass or mass flow rate of A plus C in the feed. YF, it represents mass of C divided by mass of A plus mass of C in the feed. And NF represents mass of B divided by mass of A plus mass of C in the feed. So YF is actually weight fraction of C on a B-free basis, and NF is weight fraction of B on a B-free basis. Then you have the solvent stream. For solvent, SO1, SO2, S01, S02, S03, these are solvent, or this is mass or mass flow rate of A plus C in the solvent phase. So S01, it is A plus C in the solvent that is admitted to stage 1. SO2, A plus C in the solvent that is admitted to stage 2. And similarly, you have SO3. The point is SO1, SO2 and SO3, they may be same or they may be different. Then you have X0. Even though you may have different quantities of solvent admitted in the 3 stages, its composition, its concentration is same. Same solvent is admitted to 3 stages. It may be admitted in equal quantities or it may be admitted in different quantities. So that's why X0 will be same for all the 3 stages. So X0 in this case is mass of C divided by mass of A plus mass of C in the solvent. That is weight fraction of C on a C-free basis. Then you have various overflow streams, O1, O2, O3. So O1, O2, O3, this represents mass or mass flow rate of A plus C in the overflow that comes out of each of this stage. So O1 from stage 1, O2 from stage 2, O3 from stage 3. mass if it is a batch operation, mass flow rate if it is a continuous operation. Then x1, x2, x3. Of course, x1, x2, x3, the weight fraction of C on a B free basis will be different for those stages. So x1, x2, x3, these are mass of C divided by mass of A plus mass of C in the overflow that comes out of various stages. X1 from stage number 1, x2 from stage number 2, x3 from stage number 3. Then you have underflow. You have U1, U2, U3. These are masses or mass flow rates of A plus C in the underflow that comes out of various stages. Masses if it is a batch operation, mass flow rates if it is a continuous operation. Then you have Y1, Y2, Y3, and then you can easily tell this is mass of C divided by mass of A plus mass of C in the underflow that comes out of various stages. And then you have N1, N2, N3, which is mass of B divided by mass of A plus mass of C in the underflow that comes out of various stages. So you have weight fraction of C on B free basis and weight fraction of B on B free basis in the underflow. Now let us do calculations for each stage separately. Let us start with stage 1. Let us understand what calculations are involved for stage 1. So I will show stage 1 separately. Stage 1, feed enters into stage 1. It is contacted with solvent, rich solvent, and overflow is taken out of this stage and underflow is taken out of this stage. Now you know what are the notations that I have used in the discussion. I have just told you what are the notations. Now, what happens in stage number 1? The feed solid mixture is mixed with fresh solvent. So feed is mixed with fresh solvent. And for doing calculations for stage number 1, what quantities are known to you? F is known to you, YF is known to you, NF is known to you, S naught 1 is known to you, and X naught is known to you. So this 5 quantities are known to you, and using this known quantities, we will be doing calculations for stage number 1. So when you mix feed solid mixture with fresh solvent in the stage, a mixture will be formed. And for this mixture, let M1 be mass or mass flow rate of A plus C in the mixture. Ym1 be mass of C divided by mass of A plus mass of C in the mixture. That is weight fraction of C on a B free basis in the mixture. And then Ym1 be the mass of B divided by mass of A plus mass of C in the mixture. That is weight fraction of B on a B free basis in the mixture that is formed in stage number 1. Now let us write material balance for solids. So in my discussion on single stage leaching, I have told you how to write the material balance. So you please watch the video if you have not yet seen that. So mass of B in the system, in the entire system that consists of 3 stages, this is equal to, it will be mass of B that is present in the feed. That means insoluble solid B, it will either be present in the feed and then it will go to the mixture and then it will go to the underflow that comes out of stage number 1. So that's why mass of B is equal to NF into F, that is equal to NM1 into M1 is equal to N1 into U1. I have discussed this in my last video, but let me shortly tell you. Now NF, this has units of B upon A plus C in the feed, and F is A plus C in the feed, A plus C in the feed. So A plus C gets cancelled, you are left with B. Then NM1 into M1, NM1 is B upon A plus C in the mixture. M1 is A plus C in the mixture. So A plus C gets cancelled, you are left with B. Similarly, N1 is B upon A plus C in the underflow that comes out of stage number 1. A plus C is A plus C in the underflow that comes out of stage number 1. So this and this will get cancelled and you are left with B. So ultimately you are writing material balance for B. You you are describing how B moves from feed to the mixture and then to the underflow. That's it. And I'm calling it as equation number 1. Now material balance for solute C. So it will be written as F into YF plus S naught 1 into X naught, that is equal to M1 into YM1, that is equal to O1 into X1 plus U1 into Y1, and I'm calling it as equation number 2. So how do you get this? F is A plus C in the feed and YF is C upon A plus C in the feed. So A plus C gets cancelled and you are left with, so this quantity gives C in the feed, C in the solvent. Similarly, this will give C in the solvent, C in the mixture, C in the overflow, and C finally C in the underflow. So in this way, you have to write the material balance for solute C for stage 1. And then finally, you can write material balance for the solution A plus C. And how will you write that? So it will be F plus S naught 1 is equal to M1, that is equal to O1 plus U1. And let me call this as equation number 3. F is A plus C in feed, SO1 is A plus C in the solvent. So you are writing material balance for the solution, which is A plus C. So equation 1, 2 and 3 are the material balance equations that are applicable to stage number 1. Now let us move on. Now we got this equation, mass of B is equal to NF into F, that is equal to NM1 into M1, that is equal to N1 into U1, equation 1. Then FYF plus S naught 1 into X naught, that is equal to M1 into YM1 plus is equal to O1 into X1 plus U1 into Y1. This is equation 2. And you got equation 3. F plus S naught 1 is equal to M1, that is equal to O1 plus U1. And this is equation number 3. And now what we will do, from equation 1, I will write this equation. Mass of B is equal to Nm1 into M1. So I can equate mass of B is to Nm1 into M1. And then I can write equation for Nm1. So Nm1 will be equal to mass of B upon M1. And for M1, I will use equation 3. From equation 3, M1 is equal to F plus S naught 1. So now I can replace M1 in the equation for Nm1. So using an equation for Nm1, I get Nm1 is equal to mass of B upon M plus S naught 1. So using this equation, you can calculate Nm1. But using this equation, mass of B will be known to you, F will be known to you, and S naught 1 will also be known to be. Now, from equation 2, I will write this equation. F into YF plus S naught 1 into X naught, that is equal to M1 into YM. And then I will write equation for, I will rearrange it. M1 into YM1 is equal to F into YF plus S naught 1 into X naught. And then I will write equation for YM1. So YM1 will be equal to F into YF plus S naught 1 into X naught divided by M1. And for M1, I will again use this equation from 3. From equation 3, M1 is F plus S naught 1. So that's why YM1 will be equal to F into YF plus S naught 1 into X naught divided by F plus S naught. So using this equation, you can calculate YM1. Rather, you have to calculate YM1. And for calculating YM1, everything on the right hand side will be known to you. You just have to use those values and get the value of YM1. Okay, now we will follow those material balances on the equilibrium diagram. So equilibrium diagram is plotted in this way. Nx and Ny, it will be provided to you. So you are going to plot Nx and Ny on the y-axis, and X and Y, which will also be provided to you, you will be plotting on the x-axis. Actual graph would be X is plotted against Nx. Various values of X are plotted against the corresponding values of Nx. And various values of Y are plotted against the corresponding values of Ny. So in this way, you have to plot the graph. So I will show you. So on the y-axis, you are plotting Nx and Y, and on the x-axis, you are going to plot X and Y. So you get X versus Nx curve, and then you get Y versus Nx curve. Now, in this case, X versus Nx curve is lying above the x-axis, which indicates that it is containing some solids. But in most of the cases, the clear solution, it will not be containing any solids in it, and therefore all nx will be 0 for such clear solution. In that case, x versus nx, this curve will coincide with the x-axis. So that you have to remember. Most of the time that will be true. X versus nx curve, it will coincide with the x-axis. But for the sake of understanding, I have shown a curve that is lying above the x-axis. Okay, now let us continue with the diagram. Let us do calculations. For stage 1, first thing that you have to do is you have to locate point F, and it will be located at YF So you just have to, the YF value will be known to you. So locate YF over here, this YF, draw a vertical line through it. Then NF will also be known to you. Locate NF on the y-axis and draw a horizontal line. The point of intersection of these two lines will be nothing but point F. So in this way, you have to locate point F. Then the next task is locating of point S0. So point S0 will be located at x is equal to x0 on x versus nx curve. So x0 will be known to you. Just locate x0 on the x-axis, go to the curve, and wherever you meet the curve, that will be point S0. So once point S0 is located, next task is you'll have to connect F and S0. And F and S0, they will be connected with a straight line. So F and S0, they will be connected with a straight line. Okay, so after drawing the line S0, next task is we have to locate point M1. And point M1 will be located at YM1, NM1. And first we need to find out these values. So NM1 you can find out by this equation. Mass of B divided by F plus S01. And YM1 you can calculate by using this equation. FYF plus S01 into X0 divided by F plus S01. So you can use you can use one value out of this two. You can either use NM1 or you can use YM1. So either NM1 or YM1 can be used to locate the point M1. So let us use NM1 to locate point M1. So what I will do, I will locate NM1 on the y-axis. So I have located NM1. Then after locating it, I will go to the line FS0, and where the intersection occurs, that will be my point M1. And if you get the x coordinate of point M1, that will be nothing but YM1. So in this way, point M1 can be located. Then we have to draw. The next task is to draw a tie line that passes through M1. Again, if solute C is not adsorbed on the surface of the solid, then the tie line will be simple vertical line. But if solute C is adsorbed on the surface, then surface of the solid, the tie line is not vertical, because you will have different concentrations in overflow and underflow. So it will not be a vertical line. In the first case, the concentrations in overflow and underflow, concentration of C in the overflow and underflow, they will be same. So that's why the tie line will be vertical. But if solute C is adsorbed on the surface of the solid, the concentrations of C in the overflow and underflow, they will be different. And in that case, the tie line is not vertical. And then in that case, you have to draw the tie line by trial and error. So in my discussion, in my previous video, I have told you how to draw a tie line by trial and error. So when solute C is adsorbed, you need to draw the tie line by trial and error. It depends on whether the solute C is adsorbed on the surface of the solid or not. Now let us consider the second case for drawing the tie line. So I will have to draw the tie line, the required tie line by trial and error. This green line is my desired tie line that passes through M1. I have drawn it, or you have to draw it by trial and error. So end points of this tie line, the end point, lower end point is O1 and the upper end point is U1. So endpoints are O1 and U1. The x coordinate of point O1 is x1 and the x coordinate of point U1 is y1. So x coordinate of O1 will give you x1 and x coordinate of y1 it will give you x coordinate of point U1 it will give you y1. So the objective of doing calculations for stage number 1 is to get x1 and y1, because we are going to use these values to find out quantities of overflow and underflow that come out of stage number 1. Then the y coordinate of point U1, the y coordinate of point U1 will be n1. So we may need all three x1, y1 and n1 in our calculations. So the objective of doing all this, the objective of drawing the tie line, desired tie line, is to know the value of x1, y1 and n1. So once those three quantities are known to you, you can find out the quantities of O1 and U1, calculation of O1 and U1. So these are quantities of overflow and underflow that comes out of stage number 1. So equation 2 we had written earlier, fyf plus s01 into x0, that is equal to m1 into ym1, that is equal to O1 into x1 plus U1 into y1. So from this I can write O1 x1 plus U1 into y1, that is equal to f into yf plus s01 into x0. And then equation number 3 is f plus s01 is equal to m1, that is equal to O1 plus U1. And from this I can write O1 plus U1 is equal to f plus s01. So now if you look at this equation and then this equation, you have two equations and there will be only two unknowns in this case, O1 and U1. So you have two equations, you have two unknowns, you can solve those two equations simultaneously and get the quantities of overflow, that is O1, and overflow and underflow, that is U1, that comes out of stage number 1. So with this, calculations for stage 1, they are completed. So at the end of calculations for stage 1, you know x1, you know y1, you know n1, and you know quantities of overflow, that is O1 and U1. Now we have to proceed for stage number 2. Calculations for stage number 2. So first let me show you the stage. For stage number 2, feed would be the underflow that is coming from stage number 1. That is the underflow that comes from stage number 1. And in stage number 2, it is contacted with fresh solvent. It will produce an overflow and it will also produce an underflow. So what happens in stage number 2? The underflow from stage 1, it is mixed with fresh solvent in this stage. And before you proceed for doing calculations for stage 2, what quantities are known to you? You just look at those quantities. So U1 is known to you, Y1 is known to you, N1 is known to you, SO2 is known to you, S02 is known to you, and X0 is known to you. So these 5 quantities are known to you and you will need them for doing calculations for stage number 2. So when the underflow from stage 1 is mixed with fresh solvent in stage 2, mixture is formed, and for this mixture let M2 be the mass or mass flow rate of A plus C in the mixture, Ym2 be mass of C divided by mass of A plus mass of C in the mixture, Nm2 be mass of B divided by mass of A plus mass of C in the mixture. That is, we have weight fractions of C and B on a B free basis. Then again, we will have to write material balance for solids. For stage 2, it will be written like this. Mass of B is equal to N1 into U1. That is, solids in this stream, they will go to the mixture where they will be given by this relation Nm2 into M2. Now, I am sure you will know how you get those terms. And then after out of the mixture, when the solids come out of the mixture, they will remain in the underflow. So that's why mass balance, material balance for solids for stage 2 will be written like this. Mass of B is equal to N1 U1, that is equal to Nm2 into M2, that is equal to N2 into U2, and I am calling this as equation number 4. Then we have to write material balance for solute C. and it will be written as y1 u1 into y1 plus s02 into x0, that is equal to m2 into ym2, that is equal to o2 into x2 plus u2 into y2, and I'm calling this as equation number 5. And then you have to write material balance for solution A plus C for stage 2. So it will be written as u1 plus s02, that is equal to m2, that is equal to o2 plus u2, and I'm calling this as equation number 6. So A plus C in the underflow plus A plus C in the solvent is equal to A plus C in the mixture, that is equal to A plus C in the overflow that comes out of the stage, and A plus C in the underflow that comes out of the stage 2. So in this way, you have to write different material balances for stage 2. Now let us follow these material balances on the equilibrium diagram. So before that, we will need to do some more calculations. Let me tell you what are this. Now we got those three equations. Mass of B is equal to N1 into U1, that is equal to Nm2 into M2, that is equal to N2 into U2. This is equation number 4. Then you have U1 into Y1 plus S02 into X0, that is equal to M2 into Ym2, that is equal to O2 into X2 plus U2 into Y2. This is equation 5. And then finally you have U1 plus S02 is equal to M2, that is equal to O2 plus U2. This is equation number 6. Now from equation number 4, I can write this: mass of B is equal to Nm2 into M2, that is Nm2 is equal to mass of B divided by M2. And from equation number 6, I can write M2 is equal to U1 plus S02, and then I'll use this in the equation for Nm2. So using an equation for Nm2, it will be Nm2 is equal to mass of B divided by U1 plus S02, and this is the equation that you can use to get the value of Nm2. You will need Nm2 in your calculations. Then from equation 5, you have U1 Y1 plus S02 into X0, that is equal to M2 into Ym2. That is M2 into Ym2 is equal to U1 into Y1 plus S02 into X0. That is Ym2 is equal to U1 into Y1 plus S02 into X0 divided by M2. And for M2, again, I will use this equation. Therefore, Ym2 with equation 6, Ym2 will be equal to U1 into Y1 plus S02 into X0 divided by U1 plus S02. Okay, now let us follow those material balance equations that we wrote for stage 2 on the equilibrium diagram. So I will take the equilibrium diagram that we had drawn previously. So you have this equilibrium diagram where we had drawn tie line for stage 1. Now for stage 2, first thing is in the second stage, what is done? Underflow from stage 1 is contacted with fresh solvent. So you have hence point, since you are in second stage, you are mixing underflow from stage 1 with fresh solvent. So how do you represent this operation on this diagram? You can connect points U1 and S0 with a straight line. So in order to show this, the operation in second stage on this equilibrium diagram, you just connect points S1 and S0 with a straight line. So starting from S0, I will draw a straight line, and then I will aim at the point U1. Now after that, you have to locate point M2, and for locating point M2, it will be located at Ym2 and M2, and it will be located on the line U1 S0. For that, Nm2 is required. So you can calculate Nm2 by using this equation. Mass of B, Nm2 is equal to mass of B divided by U1 plus S02. And Ym2, you can calculate it by using this equation. U1 into Y1 plus S02 into X0 divided by U1 plus S02. Either one of these two you can use. We will use Nm2. So either Nm2 or Ym2 can be used to locate the point M2. We will use Nm2. So I will locate Nm2 over here, and I will go to the line S0 U1. The intersection point will be nothing but point M2. And if I go to the x-axis, that will give me Ym2. So in this way, you have to locate point M2. Then the next important task is to draw the tie line through M2. So again, it will depend on whether solute C is adsorbed or not adsorbed. If solute C is not adsorbed on the surface of the solid, then concentrations in the overflow and the underflow, they will be same, and therefore tie line is vertical. But if solute C is adsorbed on the surface of the solid, then the concentrations in overflow and underflow, they will be different, and that's why the tie line will not be vertical. The tie line is not vertical, and in that case you have to draw the tie line by trial and error. So we'll consider the second case, and by trial and error I will have to draw a tie line that passes through M2. The endpoints of the tie line, the lower end will be point O2 and the upper end will be U2. So endpoints for this tie line are O2 and U2. Then you have to record the coordinates. The x coordinate of point O2 is x2. The x coordinate of point U2 is y2, and the y coordinate of point U2 is n2. So x coordinate of point O2 will give me x2, x coordinate of U2 will give me y2, and y coordinate of U2 will give me n2. So at the end of calculations for stage 2, you will know the values for x2, y2 and n2, because they will be useful in the remaining calculations for stage number 2. So now finally we'll have to calculate quantities of O2 and U2, that is quantities of overflow and underflow from stage 2. And for that we are going to use material balance equations. Equation 5 was written as O1 into Y1 plus S02 into X0, that is equal to M2 into YM2, that is equal to O2 into X2 plus U2 into Y2. And I can write the equation in this way: O2 into X2 plus U2 into Y2, that is equal to U1 into Y1 plus S02 into X0. And then I have equation 6, which is U1 plus S02 is equal to M2, that is equal to O3 plus U3. And from this I can write O3 plus U3 is equal to U2 plus S02. No, the equation, let me say it once again. From equation 6, I will write this equation: U1 plus S02 is equal to M2, that is equal to O2 plus U2. And then I can write it in this way: O2 plus U2 is equal to U1 plus S02. And then I have this equation. And then I have this equation. I have two equations. There are two unknowns, O2 and U2. I can solve these two equations simultaneously and get the quantities of overflow and underflow that comes out of stage number 2. So that ends our calculations for stage number 2. Now we have to proceed to calculations for stage number 3. So calculations for stage number 3. So let me show the stage. For stage number 3, the feed is the underflow that comes out of stage number 2. It is contacted with fresh solvent. It will produce its own overflow and its own underflow. So what happens in stage number 3? The underflow from stage 2 is mixed with fresh solvent. And for doing calculations for stage number 3, this quantities will be known to us: U2, Y2, N2, SO3, S03 and X0. These 5 quantities will be known to you. U2, Y2, N2, they will be known from the calculations for stage 2. Then when you mix the underflow from stage 2 with fresh solvent in stage 3, you get a mixture. And for this mixture, let M3 be mass or mass flow rate of A plus C in the mixture. YM3 be the mass of C upon mass of A plus mass of C in the mixture. And NM3 be mass of C, mass of B per divided by mass of A plus mass of C in the mixture. Weight fraction of C on a B free basis. Weight fraction of B on a B free basis. Now material balance for solids written for stage number 3. Mass of B will be equal to N2 into U2, that is equal to NM3 into M3, that is equal to N3 into U3. And I am calling this as equation number 7. So solids in the system will be solids that come with the underflow from stage number 2. Then the solids will go in stage number 3 in the mixture that is formed in stage number 3. And finally the solids will come out with the underflow that comes out of stage number 3. Then we have to write material balance for solute C. It will be written as U2 Y2 plus S02 into X0, that is equal to M3 into ym3, that is equal to O3 into x3 plus u3 into y3. Simple. C in the underflow from stage 2, C in the fresh solvent, C in the mixture, C in the overflow from stage 3, C in the underflow from stage 3, and let me call this as equation number 8. Then we have to write material balance for the solution A plus C. So solution in the underflow, that is A plus C in underflow, A plus C in the solvent, A plus C in the mixture, A plus C in the overflow from stage number 3, and A plus C in the underflow from stage number 3. So the equation is U2 plus S02 is equal to M3, that is equal to O3 plus U3, and this is equation number 6. So for stage number 3, we have to write equation 7, 8 and 9. These equations will be the material balance equations for stage number 3. Okay, so we got mass of B is equal to N2 U2, that is equal to NM3 M3 into M3, that is equal to M3 into U3. This is equation 7. Then U2 into Y2 plus S03 into X0, that is equal to M3 into YM3, that is equal to O3 into X3 plus U3 into Y3. This is equation 8. And U2 plus S03 is equal to M3, that is equal to O3 plus U3. This is equation number 9. Then from equation 7, I can write mass of B will be equal to NM3 into M3, and I'll write equation for NM3. NM3 will be mass of B divided by M3, and for M3 I can use equation 9. From equation 9, M3 is U2 plus S03, because U2 and S03 they will be known to you, and then you can use this in equation for NM3. So using an equation for NM3, I get NM3 is equal to mass of B divided by U2 plus S03. So with this equation, you can calculate NM3 that is required, and all that is required on the right hand side is known to you. Then from equation 8, I can write U2Y2 plus S03 into X0 is equal to M3 into YM3. That is M3 into YM3 is equal to U2 into Y2 plus S03 into X0, and that is YM3 is equal to U2Y2 plus S03 into X0 divided by M3. And for M3 again I will use this equation. So with equation 9, YM3 will be equal to U2Y2 plus S03 into X0 divided by U2 plus S03. So in this way we get an equation which will be useful for us for calculating YM3. All quantities that are present on the right hand side of the equation, they are known to you. Okay, so let us move ahead. Now let us follow those material balances on the equilibrium diagram. So I am taking the equilibrium diagram that we obtain at the end of our calculations for stage 2. So this is the equilibrium diagram. So in the third stage, underflow from stage 2 is contacted with fresh solvent. Underflow from stage 2, it is contacted with fresh solvent. So let us see what happens. So hence, in order to show this on the equilibrium diagram, you are contacting underflow from stage 2 with fresh solvent. Point U2 and S0, they are to be connected by a straight line. So we will connect point S0 and U2 by a straight line to show this operation. Now you have to locate point M3. It is located at YM3 NM3 on the line S0 U2. NM3 is mass of B upon U2 plus S0 3. In order to get NM3, you can use this equation, and in order to get YM3, you can use this equation. U2 into Y2 plus S03 into X0 divided by U2 plus S03. So either you can use NM3 or YM3 for locating point M3. I'm going to use NM3. So NM3 is located over here. Then I'll go to the line S0 U2. The point of intersection is nothing but point M3, and in this way point M3 has to be located. So this is point M3, and the x coordinate of point M3 is YM3. Now let us draw the tie line through M3. So if there is no adsorption, concentration in overflow and underflow, they will be same, tie line will be vertical. But if there is adsorption, concentrations in overflow and underflow, they will be different and the tie line will not be vertical. We will consider this case. So the tie line has to be drawn by trial and error. I have told you in my previous video, I have told how to draw the tie line by trial and error for single stage extraction. So here I'll have to draw a tie line that passes through M3. The endpoints of this tie line will be O3, the lower end is O3, and upper end is U3. So endpoints are O3 and U3, and we need to know the x coordinate of point O3, it is x3. X coordinate of point O3 is x3. X coordinate of point U3 is y3. And the y coordinate of point U3 is N3. So y3, x3, y3, N3, these are required in further calculations for stage 3, and in this way I get their values x3, y3 and N3. Now finally, let us look at calculations of the quantities O3 and U3, quantities of overflow and underflow from stage 3. We have to find out. So for that, from equation 8, you have U2 Y2 plus S0 3 into X0, that is equal to M3 into YM3, that is equal to O3 into X3 plus U3 into Y3. And I'll rearrange it, and I can write in this way: O3 into X3 plus U3 into Y3, that is equal to U2 into Y2 plus S0 3 into X0. Then I have equation 9, which is U2 plus S0 3 is equal to M3, that is equal to O3 plus U3. And I can write the equation in this way: O3 plus U3, that is equal to U2 plus SO3. So I have two equations. There are two unknowns, O3 and U3. I can solve these two equations simultaneously and get the values of O3 and Y3, which are nothing but quantities of overflow and underflow that comes out of stage number 3. So in this way, we end our calculations for the last stage in the cascade, stage number 3. So in this way, you have to do the analysis for multi-stage cross-current leaching. I have explained this with the help of a 3-stage cross-current leaching operation. I have told you how to write material balances for all the 3 stages, how to follow these material balances on the equilibrium diagram, then how to draw the tie lines. So with this, I end my discussion for this video. In my next video, I will solve one numerical that is based on multi-stage cross-current leaching. I hope you have understood the concepts that I have discussed in this video lecture. If you have any doubts, you please let me know in the comment section. And in my next lecture, as I said earlier, I'll be solving a numerical that is based on multi-stage cross-current leaching. So thanks for watching this video. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. For now, have a nice day and bye bye.